All right, this is a problem from our equilibrium module, and what we're trying to do is we're trying to find the equilibrium constant for this reaction, and what we know is given down below in these two reactions. And so I'm going to label this reaction 1 and this reaction 2. The way that we work this problem is very, very similar to the way that we found answers for delta H for reaction using something called Hess's law. You all did this back in Gen Chem 1. This is the same strategy. Essentially what I have to do is I have to figure out how do I manipulate reactions 1 and 2 to match the reaction that I'm trying to find the K for, because I do have equilibrium constant values for these two. So I'm going to figure out how to manipulate 1 and 2 such that they add together to give me the reaction that I'm trying to find, and then I'll manipulate the K's appropriately as indicated in the lecture material. Typically how I go about this is I just start trying to match. There's PbSO4 solid, so I look down in reactions 1 and 2, and I find PbSO4 solid. If I find it in more than one place, I skip it and move on to something else. So I'm trying to match the PbSO4 solid. That is in reaction 2. You'll notice that there's only one of it. I need one of it, and it is in the reactant side on the left, and I need it on the reactant side. So I'm going to rewrite that reaction exactly as is. I'm going to leave off the solids and aqueuses as long as I see that they match. The solids match for the PbI2, the solids match for the PbSO4, the aqueuses match for the ions. As long as I see that those match, then I'm not going to write them. If they ever didn't match, then I'd have to worry about adding them together. But since they match, I'm just going to leave everybody off. So I'm rewriting reaction 2 as is, and its equilibrium constant is, as is, 1.8 times 10 to the minus 8. Then I try to match something else. To match something else, again, I kind of go down the list. I can try to match I minus, and as I look down here in this bottom reaction, there it is. You'll notice that there's 2 of it, and I need 2 of it, but it's on the wrong side. I need it on the reactant side. Reaction number 1 has it on the product side. So I'm going to reverse reaction number 1. I'm going to rewrite reaction number 1 reversed. And there I have it. There is reaction number 1 reversed. Now, what does that do to the equilibrium constant for reaction number 1? When you reverse a reaction, it inverts the K value. Back in Hess's law problems, we would change the sign when we reversed a reaction. We also did that in the thermodynamics module here in Gen Chem 2 as well. If you reverse a reaction, the thermodynamics parameter becomes negative, the negative of it, or the opposite sign. For an equilibrium constant, the new equilibrium constant is 1 over the old equilibrium constant, or 1 divided by 8.7 times 10 to the minus 9. So that's the new equilibrium constant for the reversed reaction 1. Once I have manipulated both of the given reactions, sometimes there might be 3 that I would have to manipulate. Once I've manipulated all of the reactions that are given, I should, if I've manipulated them correctly, I should be able to just add them together to get the desired reaction. Remember that when you add reactions together, anything that shows up on both sides cancels. So my PB plus 2's cancel. That looks like the only thing that cancels. So I end up with, when I add them the reactions together, I end up with PbSO4 on the left plus 2I minus on the left is in equilibrium with SO4 negative 2 on the right and PbI2 on the right. And that is indeed the reaction I was going for, and it doesn't matter what order I put those products. Now, what happens to the K values when I add two reactions together? They get multiplied. So the equilibrium constant for this reaction is equal to my value for K2, the equilibrium constant for this first reaction I added, and the value for the first reaction times the value for the first reaction, which is 1 over K1. So if I plug in those numbers, it's 1.8 times 10 to the minus 8 divided by 8.7 times 10 to the minus 9. You should plug that in your calculator as we speak. I'm plugging mine in to make sure that you get the right answer. And I am getting 2.0689. And so the correct answer is 2.1 is my new equilibrium constant.